Today we are going to cover related rates, and this is going to be one of our tougher sections because it's an application section, but it's also going to be one of our more interesting sections because it's an application section. But we're going to spend at least 2 or 3 days going over this in hopes that we can make this as easy as possible. Okay. But let's take a look at our procedure here that we're going to follow on all these. You'll start off by drawing a picture, and I think that this can help because this gives you something to label, right? Your picture, you can put whatever your variables are that you might be working with. Okay. And once you have your variables, it's going to help you identify, what given numbers go with what variable. Okay. So it's going to help you set up your equations. Okay. And in fact, a lot of the given information that we're going to have is going to be actually in terms of rates. Okay. So when we actually go to write things, we'll be writing things like dv dt for the rate at which the volume is changing. Okay. Or dr dt, the rate at which the radius is changing. Okay. But once we're done with that, we'll have some variables that we actually want to connect. Okay. Like we need an equation that connects these things that the question's talking about. And that's what step 3 is. Okay. And this is oftentimes going to be like a volume formula, okay, or an area formula, or maybe we'll have to use a little, some similar triangles or the Pythagorean Theorem, but something we can use to connect those variables. Once we find it, we'll differentiate it, and then it'll have those rates in it. Okay. It'll have the rates that we need in it after we differentiate. And when we're done, we'll solve for the rate that we want. Okay. And right now, that probably all looks, really abstract. So I think it's going to be best that we jump right into an example. Let's read it, then we'll draw a picture, and then we'll try and write down some of the given information. Okay. So air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay. So the main words I want you to get out of this are volume and radius and maybe spherical balloon at the moment. Okay. So if we were to draw a picture of what's going on, we're just talking about a sphere. Okay. So the picture in this case is going to be one of the cases where this is actually probably a picture is not really needed, okay, but we're going to put one in here anyway. Okay. So we have a sphere. Okay. And the only measurement that we're really going to be interested in on this picture, at least, is going to be the radius here, r. Okay. So we have r here, and we know we have the word volume in there too. So we do have another variable v, but it doesn't really fit into our picture here. Okay. Well, let's see if we can write down some rates. Okay, so these rates are always going to take this form, d something dt. Okay, all right, because we're going to be talking again about rates, which is really another way of saying derivatives. Okay. So air is being pumped into a spherical balloon so that its volume, so volume is increasing. Okay. So that means it's going to be positive, whatever this number is. And the word rate, again, this is a good indicator that we are talking about a derivative. Okay. Although the units are also a good indicator. These units are in a rate. Okay. Cubic centimeters per second. That is a rate. Okay. So if we were to be thinking about the rate at which the volume is changing, we'll write that as dv dt. So the rate at which the volume is changing is that 100 cubic centimeters per second. Okay. And we're also asked to find another rate. How fast is the radius increasing when the diameter is 50? Okay. So we want to know What's dr dt? Okay. And we want to know it at a specific point in time. Okay. When d equals 50, or how about we just put this in terms of the radius, when the radius is 25. So we have our given rate, we have the rate we want to find, we have a picture. We need step 3. We need something that can relate these two variables here, v and r. Okay. All right, and so this is going to come from a formula that we actually, most of us don't have memorized, and you don't need to memorize it. Okay, but we know we're talking about the volume of this sphere here. So if we were to look up the volume formula for a sphere, we'll get 4/3 pi r cubed. Okay. There we go. Okay, and I want to ease your minds here a little bit. When it comes to, exam day, our next exam, and let's say you have a related rates question, if it does require a formula that's, one that, you probably don't have memorized, then I'm probably going to include it. So like if it was this question, I would expect most of you don't remember the volume of a sphere off the top of your head. So I'd provide this formula. But if we were talking about, the area of a rectangle, that would be a formula I'd want you to know. Okay. But yeah, if we're talking about the volume of a sphere or the volume of a pyramid, anything, really that's kind of obscure, I'm not going to expect you to remember it. Okay, but that brings us back into our problem here. We've wrote down our rates. We have an equation relating those rates. Now we need to differentiate. Okay. So the thing to keep in mind here, though, is both the volume and radius here are changing with time. These are both actually functions of t. Okay. So we are going to really be doing on all these questions really implicit differentiation, okay? Because our variables are always going to change with time. So taking the derivative of v with respect to t, nothing crazy happens here because we don't have to apply the chain rule. The derivative of v with respect to t is just dv dt. But on the other side here, we are going to need the chain rule, and this is the side where it might be a little more confusing. Okay? But I'm going to start off by just writing our constants down, the 4/3 pi. Okay? But just keep note here on the side, we're differentiating something that actually looks like this. Okay? And I'm just writing this so that it's clear that we need to use the chain rule. We have more than just t being cubed here, right? We have a function of t being cubed. So if we use our chain rule, we're going to also need to multiply by the derivative of the inside there. So r prime or dr dt there. So over here, the only thing I'm not going to do is, just so that I don't have of t floating around all over the place, I'm just going to write 3r squared dr dt. Any questions so far? Okay, well, we're actually almost done with this one. We have the equation we need here. Okay. And I suppose if we wanted to do maybe a step of simplification, we could before we start substituting stuff in. Let's maybe just do that real quick. But we could plug in our knowns and solve for our unknown right now. But I see a 3 and a 3 canceling. So this becomes a 4 pi r squared times dr dt. And if we were to plug in what dv dt is, We can see that up there at the top, right? It's 100. Okay. Let's plug that in. 100 for dv dt. We have 4 pi. We have r up here is 25. And then we have the unknown dr dt that we want to solve for here. And so if we do that, that's going to look like dr dt is equal to 100 over this 4 pi times 25 squared. Okay. And this doesn't simplify too much, but we could write this as a 1 over 25 pi. And the units here, let's see what they are. I'm going to move this up real quick. So we were talking about lengths in centimeters and time in seconds. So this dr dt should be in centimeters per second. And this would be our final answer right here. And if we wanted to find that decimal approximation, we sure could. It would be a pretty small number though, 1 over 25 pi. Yeah, it's about 0.01. Okay. All right. Any last questions about this one?
Yeah, I'm a little bit confused. I think it'll make sense the more I look at it, but why V for volume equals dV over dt, right? Because we just kind of like replaced V with dV over dt.
Yeah. This would be like, let me give you kind of a situation that looks very similar. It's because these variables are not the ones we're used to working with. But let's say you had y equals, how about just 4/3 x cubed, okay. Right? If you were to take this derivative, you would usually probably write y prime, but you could also have written like dy dx, okay? And then taken the derivative. But the point is this left-hand side, when we write its derivative, we just write the notation technically for its derivative. It's this right-hand side that we're really differentiating here.
Okay, that makes sense. So we change the notation when the right-hand side has been differentiated.
Yeah, that's right. Yeah, because we're trying to say that in this equation, this stuff on the right is equal to the volume, while this one down here, we're trying to say all this stuff's equal to the rate at which the volume's changing. So yeah, we need something different to notate that. That's a good way to think about it.
Okay, that makes sense. Thank you.
You're welcome. But one thing that is also confusing here that we're going to have to keep thinking about as we do these is these variables change with time. They are functions of time. Okay. And I also want to say this, in all these questions, we're going to be thinking about things changing with time. So we'll always be taking the derivative with respect to t. It'll always be d something dt on all these. Okay. However, you can think about things changing with respect to other things. It actually doesn't always have to be time, but that's where we're going to put our focus. We could be thinking about the height of something based on its position in the x direction rather than its time. Okay. And so we can then think about the rate that the height's changing instead of with time, but with where it's at in the x direction. Okay. We can think about all sorts of rates with respect to other things other than time. Okay. But that's all we're going to have here. So we got another one, and this one's going to be a step up. This is going to be a little bit harder, and then the next one will be a little bit tougher after that. Okay. But the first thing I'm going to sketch here for us is a bin. Okay. And the reason I'm sketching this is we have sand falling out of this bin. Let's see here. Okay. And as the sand falls out, it's going to form a pile that is in the shape of a cone, which is kind of what we would probably expect. Okay. And when we're actually thinking about a cone, there's two really helpful things to think about. One of them is the radius of the base of the cone. Okay. And the other helpful thing is the height of the cone. And right, if this was a rectangle, we'd be thinking about the length and width. Okay. So depending on the geometric object will depend probably on what variables we'll wind up using here. Okay. But let's read this and then see what we can write down. Okay. So this says sand is being emptied from a bin, and the sand is creating a pile in the shape of a cone that has a radius that is 3 times the height. So R is equal to 3 times the height. I think that might be helpful to us here in a little bit. Let's see what else we have. The height of the pile increases at 2 centimeters per second. Okay. So note the units here. Those units are telling us that we have a rate. We have a rate here. So the rate at which the height is changing is 2 centimeters per second. Okay. And this is happening when the pile is 12 centimeters high. And the last sentence tells us at what rate is sand leaving the bin at that instant. Okay. So this is the tougher part. What rate is sand leaving the bin at that instant? What concept is that? Are we thinking, are we thinking about, like, area, volume? What would this be? Velocity? What do y'all think? What are we describing here? At what rate is sand leaving the bin? Kind of tough, huh? Let's see if we can think about what it is. So the rate at which this sand is leaving the bin, okay, is going to be the rate at which the volume of this pile is changing. In other words, the amount of stuff in this pile is dependent on how fast stuff is coming out of the bin. Those should be actually the same rate. Okay. The amount of stuff coming out of the bin should be exactly how much stuff is coming into this pile. Okay. So the idea that we'll actually be thinking of will be dV dt. This is what we want to know. How fast is the volume of this pile changing? Okay. And we're told at that same instant, and that instant was when H was equal to 12. Okay. Any questions there? Okay, well, we have another formula that we're going to need that is not one that you need to memorize, but we need something that connects our variables here. We have the radius R, we have the height H, and we have the volume V. Well, that just sounds like that's probably the volume formula for a cone. Okay, and if you were to actually just Google volume of a cone, is what you'll get, okay, so what you'll get is V is equal to 1/3 pi r squared h. Okay. And these formulas, like when I was taking calculus, they were all listed at like either the front or the back of the textbook. But things are a little bit, I would say things are a little bit better here now. Let me pull up this real quick. I'm going to just go into Google here. And I want you to just see how nice these formulas pop up when you type some of these things in. So like if we were to do the volume of a cone, you can see it even gives us a nice little picture and it gives us the formula. So this is pretty nice. So for these obscure ones, this is all I'd want you to do. So if you have a question that says volume of a pyramid with a square base, you can actually, and it already started auto-filling that in for us, okay? And we can see the formula for that thing, okay? So if there's any obscure formulas as you're working through the homework, this is where I would find them. This is much more convenient than always having to, you know, open your textbook and search and hope that the volume formula you need is actually in there. All right, well, we got our volume formula. So the next step is to differentiate, okay? And the reason that we want to differentiate is we will then have dH dt's and dV dt's in our equation, okay? Which means we'll be able to find the rate that we want to find, dV dt, okay? But there's technically one thing we could do here, okay? And I want to explain why we want to actually do this. And well, I don't think it's a big deal, but this does make it easier if we do one little change to what we have here. And so what I'm trying to point out here is that this product right here is actually a product of a function of t by a product of a function of t. That would mean if we were to differentiate this, we would need the product rule. Okay? And while that's not a big deal, it's going to up our chances of making a silly mistake somewhere, okay? All right, the more complicated this is, the more likely we are to make a typo or add wrong or whatever it might be. So one thing we could do is we were given this thing right here, r equals 3h. Why don't we use that, okay? So we could rewrite v here as 1/3 pi, and in place of r, I could use 3h. And now, if the marker changes color here, there we go. Now, we don't have any r's in this equation. And that's great because you can see we didn't really care about r in the first place. It wasn't one of the rates or one of the givens. Okay? It wasn't really, yeah, it wasn't something we were concerned with. And let's keep going. If we were to try to rewrite this, we could write this as 1/3 pi. And then if you square the 3, you'll get 9. Square the h, you'll get h squared. And we still have a times h. Okay. But if I complete this simplification process here, this is going to look easy to deal with. I have a 9/3, which is 3. I still have the pi there. And then I have h cubed. So this is what we're going to end up differentiating. And this won't require the product rule. So I like this a little bit better. Okay, so let's differentiate. So if we were to differentiate, and we're differentiating with respect to t always in these questions. Okay. So we have dv dt is equal to, and we have 3 pi as our constant here. Okay. And now remember, I'll write this on the side, but I'll probably erase it here in a minute. As we take this derivative, we are thinking about that function h as a function of t. Okay. So its derivative is going to require the chain rule. And how do I know the height is a function of time? Because it changes with time. Okay, as time progresses, the height is changing. All right. And so all this is going to look like over here is 3h squared dh dt, or h prime of t. Again, those are technically both the same thing. All right. I think we can just start plugging in what we know. See what we got up here. We have dh dt is 2 and h is 12. So dv dt is equal to 3 pi times 3. H was, again, 12. And dh dt, let's move up and see it again. Dh dt is 2. So this product is actually going to be our answer here. Okay? And if we were to type this in our calculator and just multiply the 3, the 12 squared, and the 2, that's going to give us a 2,592. And then we still have the pi there as well. So 2,592 pi. And our units here, we were measuring the lengths in centimeters. Okay. And we were measuring the time in seconds. And so since we're talking about a volume changing, this is going to be in cubic centimeters per second. Any questions? All right, and let's box our answer. I'll ask one more time though. Any questions about this one?
I feel like I'm having a hard time like picturing it because I'm thinking about it from like how it would actually look pouring sand. Do I just need to like separate that part of my brain away so that I can do this?
So how do you think it would look differently?
I guess I'm just like overthinking how sand moves.
I see. Yeah, you're wondering, would like maybe the radius stay at 3 times the height?
Yeah.
Yeah, that would be the only thing that I would wonder, would that hold? But I would expect it to form a pile that looks like a cone. Yeah, the only thing I would be concerned about would probably be that one thing there is, would those ratios actually hold or not?
Yeah. Okay. But I guess since it says in that instant, so I just need to think about it paused, I guess.
Yeah. Well, so another thing is, yeah, we do need to be thinking about the instant at h equals 12, but they're telling us that this ratio is fixed. So no matter what point in time we're working with, we're being told that the radius is always going to be, yeah, 3 times the height.
Okay. Okay, cool.
All righty. Let's see here. So we got another one. Okay. And so this one here, let's start off by actually reading it. We'll sketch a picture. We'll start to fill out what we know, and then we're going to have to think about what on earth we can use to connect our unknowns and knowns. Okay. Let's see here. So we have a 5-foot tall person, okay, and they're walking 2 miles per hour away from a lamppost that's 10 feet high. Okay. And let's just sketch in that lamppost real quick. Let's see here. And let's just go ahead and maybe put little bit of yellow here at the top to kind of know this is the top of our lamppost. But it's 10 feet tall. So let's go ahead and write that, 10 feet. And it says, at what rate is the shadow of his head cast by the lamppost moving when the man is 20 feet from the post? So there's what we're really trying to figure out here is how fast is this person's shadow moving? Okay, that's what the question's actually asking. And let's also sketch in the person here real quick. And when I say sketch in the person, I'm going to sketch in a line. So here's a line. Okay, and hopefully it looks about half the length. I'm going to write 5 feet here. And the idea is the light coming from this, the top of our shadow is going to create this triangle here. And let me use the line tool though, so it looks a little cleaner. Okay. Now we're just going to go from here to the ground. Okay. So wherever this line ends is the end of our shadow. Let's say right there. Okay. Okay. But the important thing to note here is this does form a triangle. And in fact, it forms 2 triangles. Okay. There we go. So I think having this in here is going to help us label some more things. Okay, I wanted to get this full triangle here real quick. So if we were to read this again, now a 5-foot tall man walks at a rate of 2 miles per hour away from the lamppost. Okay, so when we're talking about this person moving away, we're talking about this side length right here changing. Okay, and by this side length, I just mean from here to here. Okay. So when we're talking about this person's speed, how fast they're walking, we're just really saying how fast is X changing with respect to time. Okay. And it's that 2 miles per hour. Okay. Okay. Let's see what else we have. At what rate is the shadow of the head cast by the lamppost moving? Okay. So is what we're thinking about now is how far is this end, or how fast, not how far, how fast is that end arrowed to moving from this end? Okay. We want to know how fast is that shadow going? Okay. Well, that means we need to be thinking about how fast this big side length here is changing. There we go. Okay. So I'm going to write in here that we would like to find dz dt. Okay. And this would be when this person is 20 feet from the post. So that would be when x is equal to 20. Okay. So I want you all to stare at this triangle that we have for a second. Okay. And I know that some of you have had high school geometry much more recently than others. Okay. And so I'm hoping that maybe somebody can tell me, what does this picture that we just sketched here remind you of from high school geometry? This picture here, just the triangles.
A right triangle.
These are both right triangles, that's true. And let me go a step further. Let's note that this big triangle and this small triangle,
they're similar?
Yeah. Yeah, we have these 2 triangles that actually share an angle here. Okay. And yeah, these, in fact, they share all their angles. This is right, this is right. Okay. And this would be 90 minus theta, whatever that happens to be. Yeah, these are similar triangles. Okay. And I'm going to get rid of all this mess here real quick, but that's what I wanted to point out was we actually have similar triangles here. There we go. Okay, so let's set up those equations. Okay. So when you do have similar triangles, it means if you were to take ratios of the sides of the big triangle and compare those same ratios for sides for the small triangle, this should give you actually the same number. So in other words, if I were to make a fraction maybe based off the big triangle, like take the height and divide it by the base, I should get the same thing if I were to take the smaller triangle and do its height divided by its base. So its height is 5, but the question is, well, what's the length of its base here? Can you tell me what the length of the base of this smaller triangle is? You'll have to write it with letters though.
Z minus
x.
Yeah, z minus x, because the whole length is z, and it's x units up to here. So what's left must be z minus x. All right, so we had to use similar triangles here. So let's write that actually up front here so we don't forget where'd this equation come from. Similar triangles. And I'm just going to scoot this up my equation over just a little bit. There we go. Now, is what we learned when we were doing the section on implicit differentiation is that we can really find the derivative for the equation no matter what form it's really in. So is what I'm trying to say is we could differentiate this thing right now, or we could move stuff around a little bit and then find the derivative. Okay. And I would really recommend that because this derivative doesn't look like it would be very fun. All our variables are in the denominator. And I don't want to differentiate that. Well, let's cross multiply. So if we cross multiply, we'll have 10 times z minus 10 times x. So I just multiplied the 10 by z minus x. And then on the right, we'll do 5 times the z. Okay. So 5 times z. And let's keep moving stuff around. I'm going to actually isolate z. I want to find dz dt, right? Let's just isolate z now. Okay. Sometimes this isn't easy to do, but here it's not going to be bad. So if we subtract by 5z, we'll get a 5z here. Minus 10x equals 0. Okay. We could add that 10x to each side. And then we could divide by 5. And so we just get z is equal to 2x. And so this is actually going to be the easiest derivative we've had yet to do today. Because neither the z or the x is being raised to a power. Neither one of them is being plugged into any functions. So that means we won't have to actually think about the chain rule for this one. This is the only one so far, and the only one we'll do today where we don't have to think about the chain rule. So dz dt is equal to 2 times the derivative of x with respect to t. And all we have left to do is plug in what dx dt is. Let's go up and see what that was. It was 2. Let's plug in that 2. So that gives us 4. And our units that we were using to describe speed here were miles per hour.
What about the 20?
So good question. So something happened here. So sometimes after you take the derivative, you might still have like X's and what else did we have? Z's. You might still have like X's and Z's over here, but don't write this, that what I just wrote here with the X plus Z. Okay. But the point is, if our derivative still had these X's and Z's here, we'd have to come in and plug something in place of these. Okay. But sometimes our derivative isn't going to include those extra variables. And so sometimes some of these won't be needed. Okay. But there's even more that could be said about this. Okay. So even though we didn't need this X equals 20, okay, is what it means that we didn't need X equals 20 is that this shadow is actually moving at the same rate all the time. Okay. Or actually, I want to reword that. Okay. Is what this is telling us is that the rate at which this shadow is moving doesn't depend on the spot where this person is. Okay. In fact, the only thing that it depends on is how fast the person's moving. Okay. Which is another way of wording what I said first, which is that the rate at which this shadow is moving is the same no matter actually where this person is. Okay. And this is not something that I think is intuitive, and sometimes it's calculations like this that we need to make sense of some not so intuitive results. Any other questions about this one? And I'll box our answer here too.
I'm just a little confused why, if the man is walking 2 miles per hour, why wouldn't his shadow be moving at the same rate as the man? Like when I first read this, I was like, isn't the answer just going to be 2?
Yeah, so the thing is, how do I want to say this? So I do want to say again that I don't think it is super intuitive, right? That this would be the answer for 1, but for 2, the thing is our shadow, right? Depending on where we are in terms of the light, right, is going to be various lengths. Okay. Right? Like the further you actually go from the light post, right, the actual bigger the shadow is going to be. And so I think it's actually really hard to try to imagine what the length of the shadow would be, or the rate at which the shadow is changing because of that. Yeah, I feel like it would be really hard to guess here. Because when you're really close to it, your shadow is really small. When you're really far, the shadow is really big. This is non-intuitive.
Okay.
Yeah, and there's actually, I want to say one more thing to that. There are all sorts of really cool, non-intuitive things that we'll get to see in calculus. And I hope I'm not getting this backward, but like there's one thing in calculus 2, and it's called Gabriel's horn. Okay. And what it is it's a function, and when we go to compute its volume, okay, I believe it's the volume comes out to be infinite, but the surface area comes out to be finite. Okay? Because this horn that we're talking about is actually going to be of infinite length. But when we go to make those calculations, it's really interesting that one calculation comes out to be infinite and the other one comes out to be finite. So this won't be the last time where we'll see a result and we'll be kind of shocked by it. They won't all be that way though. We won't always be shocked.
If we had used the 20 feet from the post, would we have completely done it wrong? Like if we substituted that in for x.
So there wasn't an x left. So yeah, what the issue is yeah, our derivative just didn't have any x's in it. It had a dx dt,
okay,
but no x's.
Yeah. I was thinking about it like substituting it in way earlier, but now I understand.
Oh yeah, so another common thing is yeah, kind of substituting these variables in a little bit too early. I would avoid trying to substitute stuff in until after the differentiation.
Okay, gotcha.
There are some exceptions to that rule, like up here. We didn't substitute in a value though, I want to point out. Like here we substituted in r equals 3h before we differentiated. But no, again, this wasn't a number that we plugged in. And the reason we want to avoid plugging numbers in at this stage here is these variables that we're talking about are changing. So if we say that they're a constant, then when we go to differentiate them, we're treating them as constants rather than as variables, and it'll mess things up. Okay. And we have about 4 minutes left here, but what I'm going to do is I will actually probably go a little over today just so we can finish this one. Okay. And I'm actually recording what we're doing today, so you'll be able to go back and look at this if any of you have to leave before we finish it. But I don't think this one will take us an extraordinarily long amount of time here. So if any of you want to hang out for maybe an extra 5 minutes after class, you can. Let's take a look. So this is our last one of these. We have 2 boats leave a port at the same time. Okay, and we have one of them is traveling westward, so to the west. Let me see if I can get this line tool to work. There we go. So we'll just call this boat 1 maybe over here. We'll call this the port. Okay. And let's sketch in one more boat. The other boat in the directions here say it is traveling southward. Okay. And so note, if one's traveling west, one's traveling south, we actually have a 90-degree angle here. And in fact, we have a triangle. Okay. And before we go any further, let me just point out that this was boat 2. Okay. And also let's note that, well, this distance here, let's just call that x, because we usually call that the x direction. And let's call this length over here y, or this distance y, because we usually call that the y direction. Okay. And now let's fill in the details. So one boat travels 20 miles per hour westward. Okay. So the rate at which this side length is changing is 20 miles per hour. Okay. And if we were to look at the next piece of information, the boat heading southward is going 15 miles per hour. So in other words, the rate at which y is changing is 15 miles per hour. Okay. And the question is how fast is the distance between these two changing? Okay. Let's call the distance between these two capital D. All right. And we're actually told to find the rate at which that distance is changing when 30 minutes have passed. Okay, and notice that we're measuring time in hours here. So I'm going to say, instead of 30 minutes, I'm going to just say a half hour. And we actually have pretty much the setup here complete. We just need an equation now that would relate x, y, and d for a right triangle. And that is going to be our Pythagorean theorem. And so this looks like x squared plus y squared is equal to d squared. Okay. And so we're going to differentiate this. So we'll get a 2x. Okay. And remember, x is a function of time. So I need to tack on a dx dt here. And also remember, y is a function of time. So I need to tack on a dy dt. And the rate at which the distance is changing, or the distance between them is also changing with time. So I'm going to need a 2d dd dt. And let's pause for a second. Are there any questions about what we got here so far? Okay. Well, then what we're going to do is we want to solve for dd dt. Let's divide each side by 2 since all three terms have a 2 in them. And so that's going to look like 2x dx dt plus, oh, I said I was going to divide by 2, right? Let's do that. So how about x dx dt plus y dy dt is equal to d dd dt. And is what I'm going to do right now is let's just divide each side of the equation by d as well. So if we do that, then we just have dd dt is equal to x times dx dt plus y dy dt over d. And I want you all to note something here. We have dx dt, dy dt, but we don't know x, y, or d. Okay. But the big question is well, x, y, and d, they're different values at different times. Okay? But the point in time that we're concerned with is after that half hour. And we can actually make a triangle that looks just like the one above, but for a half hour. Okay? Okay, so there's the triangle. So this boat, you might remember, is traveling 20 miles per hour. So if they only go for a half hour, they will have went 10 miles. And the boat going south is going 15 miles per hour. So they'll only go 7.5 miles in that half hour. Okay. And if we wanted to use our Pythagorean theorem here to find d, let's just note that this was x, this was y, and to find d, we just want to do the square root of the 2 legs squared, 10 squared plus 7.5 squared. And if I were to calculate that real quick, our 10 squared plus 7.5 squared, this gives us that d is equal to the square root of 156.25. Okay. And so now we do have x, y, and d, and we can substitute all these into this equation up here, and we will be able to get our answer of how fast are these two boats traveling from each other. So x, we said, is 10. dx dt is 20. dy dt, or sorry, let's start with y. Y is 7.5. And then dy dt is 15. Okay. And capital D here is the square root of 156.25. And if we were to plug this into our calculator here, we actually are going to get 25. It comes out to a nice number, 25 miles per hour.